So now we know how to model our generation capacity. Okay, I hope that you are all experts in calculating the capacity outage probability table. We learned the recursive algorithm. We know how to deal with binomial distribution, right? So as long as components are identical, you can use binomial to get the COPT, but usually they are not. Especially in a large part system, they will not be. So therefore, you must use the recursive algorithm. Now, we have two types of reliability evaluation techniques, analytical techniques and simulation techniques. Again, what are we after now? We are wanting to go towards finding the risk in the system. How do we define the risk? How do we quantify the risk? It is in the form of loss of load expectation, loss of load probability, loss of energy expectation, and things like that. I gave you a list of 7 or 8 reliability indices. You can find any of them. Yeah.
In the previous question, by using the cumulative probability, how can we draw the conclusion? Just referring the previous example where we were having 20 megawatt generator and 140 megawatt.
Correct.
We draw the chart of the cumulative probability.
Yeah.
Now, what conclusions can we draw from?
Yeah. So from that table itself, you cannot draw any conclusion because the conclusions are drawn from the risk rather than from the capacity model. So you will be able to see.
In conjunction with some other model also.
Sorry?
That cumulative probability shall be used with some other tools also to draw any conclusion.
Yep, that's where we are headed now. Yeah. Thanks. So there are two types of calculation techniques to calculate the risk. That's what I'm saying now. One of them is called the analytical techniques, which is what we are focusing on, and the other is called as simulation techniques. The analytical techniques evaluate the reliability indices using mathematical models. And of course, we know by now that we make many approximations, many assumptions when we derive these mathematical models. So the answer is also not very accurate, but still we believe that it is the best way to do it rather than to make the model so complex that even the result may not be any more meaningful. The other method is called the simulation technique, and usually we use Monte Carlo simulation. Some of you might have used it in your own research. It's a very elegant tool, and more often than not, the way it started in reliability evaluation, it was used more in Europe, whereas in North America, more analytical techniques were used during the time that I was a student. Of course, now things have changed. Now the computing power has increased tremendously. So therefore, both the techniques are equally popular everywhere. But there are problems with both the techniques. As I said, for analytical techniques, you can only calculate the expected values. You don't know the probability distribution of those numbers. Like LOLE, we are going to find the LOLE. But is it described exponentially? Is it described Weibull in a Weibull, Rayleigh, or normal way? We don't know. That's not what the analytical technique tells us. Whereas the advantage of the Monte Carlo simulation is that it will give you the probability distribution as well. However, there are also disadvantages there, because depending upon the technique, and there are two types of simulation techniques, non-sequential and sequential. Non-sequential considers each time interval independently. So that's why it's called non-sequential. There's no sequence. You take every time interval as it is. Whereas in the sequential approach, you take each time interval in a chronological order. Both the techniques exist depending upon the application. One type is more powerful than the other. But it has also got some problems, because if you observe this paragraph, says one problem inherent in all simulation techniques is that a specific solution is not arrived at. The solution is dependent on the number of experiments, the number of simulations, you call it experiments, and usually sometimes you have to run the simulation for 100,000 times. Some of them, simpler ones, maybe 10,000 times, but the larger the number here, the greater the accuracy in the end result. It is also dependent upon the starting value or the seed value that you use in the simulation and the sequence of random numbers generated. So random number generator also becomes important, right? So we can't keep saying, oh, there are limitations here, there are limitations there, then what the hell can we do? We can't use anything, right? So we might as well use something that gives us a reasonable answer, especially when we are doing long-term planning. Anyway, there will be so much uncertainty in it. Maybe you got to revisit that every 2-3 years to modify your plan. Yeah, make sure that you are going with the times. Yeah. So there are these two types of techniques. I just want to tell you that there are these two types, but our focus today in this course is on analytical methods, okay? Simulation methods, you will definitely need computers. There's no way I can teach you just like this using simple examples. So we are now moving towards the loss of load expectation evaluation using the analytical technique. So in order to do that, I will need the second model, which is the load model, right? We have talked about the generation model, but we haven't talked about the load model. So let's look at the load model. There are two models that are commonly used. Both are sort of related, but one of them deals with the daily peak load. One of them deals with the daily peak load. So, you know, Monday, the peak load is this much. Tuesday, the peak load is this much. You don't consider the load hour by hour. You take just the maximum load on a particular day, and we use that. And then we arrange them in a chronological order, in a descending order, and then that curve is called the daily peak load variation curve. The other curve is the load duration curve. Load duration curve takes the hourly loads and then arranges them in a descending order. So one deals with hourly loads, the other deals with daily loads, right? But if you look at the load duration curve, because it deals with hourly loads, the area under this curve is actually the energy required by the load, because it deals with hourly, megawatt hours, kilowatt hours, gigawatt hours, you will get directly. Whereas if you use the daily peak load curve, it's not going to give you exactly the energy. Yeah, it's the load is in on a daily basis, so it gives you in days, megawatt days, gigawatt days, not in megawatt hours, right? So that's not a true representation of the energy required by the load. So that's why whenever energy calculations are needed, we use the load duration curve. But if you are only after the loss of load expectation, you could use either. And I'll show you the use of both of them, hopefully. One through an exercise and the other through an example, okay? So the typical shapes of these two curves are shown here. The daily peak load variation curve, the load duration curve, and this is the time in per unit. It could be like over a month, it could be over 6 months, it could be over 1 year. So if it is 1 year, then this one represents 8,670 hours or 365 days. So for the daily peak load variation curve, it could be 365 days, yeah? Or for the load duration curve, it could be, if you are doing it for the whole year, it could be 8760 hours. If you are doing it for a month, it is 720 hours, okay? 24 times 30. So in the analytical approach, we use the COPT and we combine it with the load characteristic to get the risk. Yeah, as simple as that. So you will see through calculations, it's not that hard at all. But before we use the COPT, you must realize that there is a difference between the terms capacity outage and loss of load. Yesterday I told you that when we develop the capacity outage probability table, we should know what is loss of load, correct? That means whenever the capacity becomes less than the load, after you have considered all kinds of remedial actions, support from interconnections, voltage reductions, voluntary load curtailment, and so on and so forth. And still, if your capacity is less than the load, then you will curtail load, you will cut load. So that situation is loss of load. But capacity on outage may not result in a loss of load, right? Suppose my installed capacity is 10,000 megawatt and my peak load is 7,000, and one of my generators, 1,000 megawatt, goes out. I still have 9,000 megawatt. Therefore, there is no loss of load. So we must make sure that we understand these two terms correctly. So the term capacity outage indicates loss of generation which may or may not result in a loss of load. Yeah, it could, it may not, okay? So loss of load only occurs when the generating capacity is less than the load. So now let's try and understand this from this particular figure. From this figure, you notice that this is the daily peak load variation curve over 365 days, for example. And this is the installed capacity in megawatt. This is the reserve in the system, because anything greater than the peak load is obviously the reserve in the system. And suppose there is an outage O subscript K. O stands for capacity outage, outage. And K means it could be outage 1, outage 2, outage 3, where K goes from 1 to whatever. How many states are there in the capacity model? That's what K goes from, yeah? So suppose there is this outage O subscript K which happens to fall here. Obviously, we are not able to meet the entire load, are we? We are not able to meet the entire load, isn't it? Because the peak load is here and my capacity outage is this much. So I only have this much capacity, correct? I only have this much capacity. So how many time units I am not able to supply the load? I repeat, how many time units out of 365 days I am not able to supply the load? We need to calculate this using the daily peak load variation curve, or the data which you have arranged chronologically or in a descending order. So when you have got a computer program, that can be done very easily. For us, because we can't use computer programs here, so I'm going to assume in an example very soon that this is a straight line. That makes my job easier, your job easier, right? Because everybody can then write the equation of the straight line, and then we can find these time units very easily. Right now you can't. When it is a curve, then you can't, right? You need all the data, every day's data. Whereas when it is a straight line, we don't need that, okay? So this is how we will find for each OK, we will find TK. Then we will go to the next outage, we will find the next time. Next outage, we'll find the next time. And how do we find the LOLE? What is LOLE? Loss of load expectation. Remember the key word, expectation. On the first day, I told you that expectation is nothing but the mean, correct? Basically, the word expectation is the same as the mean. So, in other words, if I have so many scenarios, O1, O2, O3, O4, T1, T2, T3, T4, if I do an expectation, what will I get? I will get the probability of this times the time units. So I'll have P1, P2 plus P2, T2 plus P3, T3, etc. And that will give me the risk in the system. So the loss of load expectation is nothing but PK, TK time units, where K goes from 1 to N. Very straightforward. You know the probability of each outage, don't you? From the capacity outage table, you already know PK. You need to find TK, yeah, using this sort of a notation. So whenever there is an outage, you find the time units that we are not able to supply the load, either using a software or using the equation of the straight line, or any other format in which the load curve is given to you, okay? It's not an instant, it's a period. It's a period, yeah, it's not an instant. See, we are not able to supply the load for this period, isn't it? Yeah. So it's a period, it's not an instant, correct? So this is the equation for LOLE, summation PK TK. We can also use the cumulative probabilities. It's a question that you have been asking, how do we get this into play? We can use the cumulative probabilities, then the LOLE will be capital P uppercase PK times TK minus 1. So then you have to find the difference of the time units because you are using cumulative probability. Yeah, so if I go back to this one, suppose this is T1 and then we'll have a T2 here. So if we use cumulative probability, it will be T2 minus T1. It will be the difference of the time units. Yeah, we'll see the example and then I'm sure you will understand it better. So if the load characteristic is the load duration curve, the units for LOLE will be in hours per period. If the period is a year, hours per year. If the period is a month, hours per month, yeah, and so on. And for a daily peak load variation curve, it will be in days per period, obviously, correct? And the period of study could be a week, a month, or a year. And we could even include generator maintenance and generators being decommissioned, new generators being added. We can include all of that in a more detailed study, okay? So let's look at an example. Nothing better to understand than by use of an example. The application of equation 7.1 and 2 can be illustrated using this example. 5 40 megawatt units each with a forced outage rate of 1%. So you can use the binomial distribution to calculate the capacity outage probability table, right? So that's what I have done. Further, I have stopped here. Why did I stop here? Because actually this should go up to what? 40 times 5 is 200. Actually it should go next 160, then 200, right? And the probabilities will be very, very small. So I am ignoring or neglecting all the probabilities below a certain value, that is below maybe 10 to the power minus 6, if I'm not wrong. I must have mentioned somewhere, yeah, below 10 to the power minus 6 have been neglected. If you don't want to neglect, be my guest. These days calculators have up to 14, 15, 16 decimal places, so go on, do it. The result will be different in the 8th or 10th or 11th decimal place. Big deal. Yeah. So really, we don't have to be so specific, right? Just stop at 10 to the power minus 6 or minus 8, whatever you feel comfortable with. Okay, so our daily peak load variation curve is given by this straight line between the 100% peak load percent. So this is given in percentage, and the 40% peak load. Yeah. So what does the 100% represent here? Yeah, the peak load is 160 megawatt. So this is 160 megawatt, and this is 40% of 160, so 64 megawatt. Okay, you can do it in megawatt, you can do it in percentage. It's up to you. I think everybody knows how to write the equation of a straight line, so I'm not going to dwell on that. Okay, y is equal to mx plus c, where m is the slope, and the slope is y2 minus y1 over x2 minus x1. So you can actually easily calculate the slope. Okay, and then calculate for any value of y, you can calculate the x. That's what we are after, right? Remember I told you I want T1, I want T2, I want T3. What are those values? T1, T2, T3, they are x. Y is equal to mx plus c, they are x, right? And of course y is the corresponding value here, corresponding value here, corresponding value here. The slope is easily determined, okay? So we use 7.1 or 7.2. You can use both individual and cumulative probabilities. So I just want to illustrate using this graph again how the calculations are done. So our installed capacity is 200 megawatt. Our peak load is 160 megawatt, correct? Right? Installed capacity is 200, 5 generators of 40 megawatt each, and the peak load is given as 160 megawatt. So if none of the generators is out, we have 200 megawatt, we are able to meet the load, right? So there is no loss of load, correct? That equation, if I use that equation Pk, Tk, yeah, the time unit is 0, right? So that first thing, when there is no outage, no generator is out, that is Pk, Tk is 0, right? Then the next one, the next outage is 40 megawatt, right? How many states are there? We just use this table, right? 0, 40, 80, 120. We are stopping at 120, right? So to make things easier. So 40 megawatt out, I know the probability. I also know the cumulative probability, but I'll come to cumulative later. For now, I'm just using the state probability. So I know the probability. What do I need? I need T2. I need the time units corresponding to 40 megawatt out. But I look at this, 40 megawatt out means I'm still able to meet 160 megawatt, correct? So therefore, I'm not losing the load at all. Yeah. So that number will also be 0. That number will also be 0. The time units 0, 0. Can you see that? Tk for the first outage, meaning no generators out, is 0. Tk for the second case, one generator out, 40 megawatt, is still 0, because we are not losing load. There is no loss of load. Clear? Then the third case, when 2 generators are out, we lose 80 megawatt. Then of course 80 megawatt is here, and this is my load curve, and I'm not able to supply the load for this time T3, small T3, okay? I'm not able to supply the load for this small time T3. So you can calculate this time using y is equal to mx plus c, yeah? And you will find that it is 41.7% in terms of percentage. Okay, so then the next outage will be 120 megawatt, and then you can find this T4, small T4, yeah, again using the equation of the line. So actually we have all the T's and we have all the P's, and all we need to do is now P times T and PK, TK, and then add them all up, and you'll get the risk in the system. Okay. Now I mentioned about the cumulative probability, so I think we can use the same figure to even look at cumulative probability. So what happens when the outage is 80 megawatt? We are going to use uppercase T3, which is small t3 minus t2, but there is no t2, t2 is 0. Therefore, outage, it will be 41.7 minus 0, so it will still be 41.7. But for the 120 megawatt out, we have the small t4 and small t3. Therefore, the difference of the two is t4 minus t3, which is uppercase T4, which also happens to be 41.7%. So that's how we will do the cumulative probability table and calculate the risk. So this is the calculation of the risk. We know the individual probability, we know the TK, so we can calculate LOLE, which is PK, TK, and this is what we get, but this is all in percentage. So we need to eventually multiply it by 365 days, yeah? And because it is percentage, we need to divide by 100. So you will get 0.15 days per year, because the period was supposed to be 1 year, 365 days, so it is 0.15 days per year. Remember that reference that I have been talking about, 0.1 days per year, so this is 0.15, pretty good, yeah? If the cumulative probability values are used, then this is what the table will look like. We know the cumulative probabilities, yeah, I know by now you all know from the state probabilities how to determine the cumulative probabilities, and then the uppercase T, so this is cumulative probability, uppercase P, uppercase T, for the first two cases 0, third case it's the small t3 minus 0, and for the fourth case it's small t4 minus small t3, which also happens to be 41.7. Do the same thing, PK, TK, and you will get this multiplied by 365 over 100. It's the same result. The loss of load expectation is unique, okay, 0.15. Very soon we will see what happens to this value when we include uncertainty. We have been talking about the uncertainty, and we also spoke about the probability distributions on day 2. And one of the probability distributions we learned was the Gaussian or normal distribution. So we'll see an application of the normal distribution today, okay? Any questions about the LOLE calculation? This is the risk in the system, okay? So if you want to use the cumulative probability, and if the load, now I'm assuming now a very pessimistic situation. Now let's go back to what is our goal. Our goal is to do long-term planning. Yeah, long-term planning. Adequacy. Remember adequacy and security? I'm after adequacy, not security. Adequacy means existence of sufficient facilities of generation, transmission, distribution to meet the load demands at some time in the future. So you are doing future planning, right? So when you are looking at the future planning and you say that the load is like this straight line, somebody can argue, why are you trying to make things so complex? Why not assume the load to be constant? I'm 15 years away from today. Can I say that the load will be like this? Yeah, why not just take a constant value? Take different constant values, find out the implications, and then decide, you know, where you want to stay, how much you want to reinforce the system. That's one way of doing it, yeah. So if the load is assumed to be constant throughout the time period considered, that means 160 megawatt, not like this, but like this, right? 160 megawatt. So if that is the case, then we can use the cumulative probability of the first negative margin, first load loss state, to get the LOLE. That's the advantage of the cumulative probability capacity table, which I also mentioned yesterday. So if you look at the cumulative probability table, assuming the load to be constant at 160 megawatt, so when we have 40 megawatt out, we are still okay, correct? When we have 40 megawatt out, we are still okay, no loss of load. When we have 80 megawatt or more out, then the cumulative probability is 0.000980, correct? So if the load is constant at 160 megawatt, my loss of load expectation is 0.000980, of course as a percentage. So you need to multiply it by 365 and this is what you get. So the risk in this system is 0.35 versus 0.15, more than double. But when you are comparing alternative options, the numbers don't mean much, right? Because you are going to compare the alternatives and see which one is probably best for your own system. But we have at least an analytical method to calculate and to give us the quantitative reliability indices for which we can base our judgment, right? Eventually, of course, you still have to use your judgment, but at least you have the basis for that judgment, okay? So that's what we have done now. We can use any of the load curves, but constant load gives you a pessimistic appraisal. Pessimistic, obviously, you can see the number is much higher, yeah? 0.35, which is almost more than double of the number that we obtained using a load curve, straight line curve. So while the load is not expected to remain constant, for planning purposes, a single load level may be adequate, especially when you are comparing alternative strategies, alternative options. That's all I'm saying. So you have the option. You want to consider the load curve, which is so uncertain in the future, you can do it. Alternatively, just use a constant load level. You get an idea of what kind of risk will exist in the system. It may be a pessimistic appraisal, but isn't pessimistic better than optimistic? Because the load is likely to be much more than what you are expecting it to be, isn't it? So we are better off with a pessimistic appraisal in many ways. So there is an exercise for your doing pleasure, as always. So I have given you the hourly load data for 24 hours. Yeah, it's actually very simple. And I have even drawn for you the load curve, the load duration curve over a 24-hour period. And I'm asking you to calculate the LOLE. Let's read the question. 425 megawatt, 1% forced outage rate unit with the load data given in table 7.4. The load duration curve is given in this figure. The objective is to determine the risk. Okay. So what is the total capacity? 100 megawatt. Yeah, you can find the capacity outage probability table using binomial. Yeah, and then you can combine it with this load. You see the loads here. I didn't draw the curve for you initially, but later I said, okay, let's make your life simpler, nicer. So you see the maximum load here. You just look 74. Yeah, maximum load is 74, right? Is it? Am I missing something? Oh, yes, 82, yeah. I'm not getting any younger. So 82 is the highest load and 32 is the lowest. So here it is, 82, you're right. 82 all the way up to something like 32 or 34, whatever it is. So hourly, right? It's changing hourly, correct? So it's not like a straight line. You can approximate it using, your least error squares algorithm and things like that by a straight line if you want. But it's 24 hours. It's not 8760 hours. So it's very doable by hand calculations. Yeah. And if your load is 82 and the installed capacity is 100, so you are somewhere here, right? So if one generator goes out, 25 megawatt, you only have 75. You're going to lose load, correct? So how many hours are you going to lose load? You can just go here, you'll find it is 1 hour or 2 hours. And then you do LOLE is equal to PK, TK. That's it, very simple. I've given you the answer. It shouldn't be a problem, 0.049 hours per day. Because the data is for 1 day. So it will be hours per day. I remind you again, this is a time unit, this is a time unit. You can actually convert the hours to days. So it will be days per day. And then what will you get? Loss of load probability, LOLP, right? The two are related. However, this is more meaningful. You and I can relate to it, right? How many hours am I not going to get supply today? 0.049 hours, right? Whereas if I say the probability of not being able to fulfill the load today is 0.98, that is not so meaningful, right? So the two are related and yet this is more significant. Okay, now we have shown some studies. We know now how to calculate the risk in the system. Let me show you what happens when we change some of the parameters. Because when you do long-term planning, you don't know the forced outage rate of generators. Yeah, you probably can only think of the capacities of the generators. Even those may be derated, like a 40 megawatt generator 10 years down the road. Maybe it will not produce 40. Maybe at most it will produce 35, 36, 37 megawatt. So how do you include all those parameters in your calculations? So I'm going to show you some of them. Changes in peak load, changes in the unavailabilities of the generators. How do they impact the risk in the system? That is what we call sensitivity studies. That's the advantage of any research. Once you have the algorithm, once you have the program or whatever you are using, you just vary the parameters and see how it impacts the output. So that's what I'm going to share with you. So the system risk for a given capacity composition is dependent upon the unavailability values of the generators. How? We'll see shortly. Alternatively, I can also argue that the risk is dependent on the peak load, isn't it? Just now in the example, we saw that the peak load was 160 and the installed capacity was 200, right? So if I change the peak load, do you think that the risk will remain the same? Generally, you would expect that if the peak load increases, the risk will also increase. And if the peak load reduces, the risk will also reduce. So you have a way to quantify those things through these techniques. Intuitively, we know which way it's going to go, but how much, we don't know, right? We can only use these algorithms. So let's go back to this system with 540 megawatt units, 1% forced outage rate, and we change the peak load. Yeah, so we change the peak load, and you see 160 megawatt peak load, this was our risk, remember? From the previous example, we found the risk to be 0.15. Now I change the peak load 200, the risk becomes 6 days per year. And if I reduce the peak load to 100, it's only 0.001 days per year. So you can see the variation. Now we can quantify the risk. Are you, as a management or as a manager or the boss of the company, of the organization, are you willing to accept that this will be the peak load and this will be the risk? Or you think that the peak load will become higher and therefore the risk will be this, and therefore you want to mitigate the consequences of that risk level. So that is where the engineering judgment will come in, of the planners, operators, managers, and so on. So this forms a very good basis when we do sensitivity study. So this is with the peak load. We can do another sensitivity. So this is just showing you in a graphical way, the loss of load expectation here versus the peak load. So you can see 160 is where we were, 0.15, the risk was 0.15, yeah. So as the peak load increases, the risk becomes higher. It goes up to 6 days per year, remember, from that table. Now we change the forced outage rate of the generators. We change the unavailability of the generators, because that's also not known to us. In the years to come, we expect that, okay, the manufacturer is telling us based on past data that the forced outage rate of this generator will be 1%. But we know that it is uncertain. So we can also include that uncertainty, change the forced outage rate. When it was 1%, our risk was 0.15. If it goes up to 5%, the risk will be 3.6 days per year. So we can quantify everything. Where do you want to draw the line? It's entirely up to you. If you think that it will drop to such an extent, then you need to be prepared for this risk in your system. Are you going to do anything about it by adding more generators, yeah, or reinforcing the system in other ways, or not? Maybe you want to allow the system to degrade, yeah, because there is still uncertainty. Maybe it's not going to go to 5%. Maybe it'll only go down to 2%. So you have to decide. That managerial decision is still in the hands of people. We can't let the computers decide that for us, okay? So we can see that based on these two parameters, the peak load and the unavailabilities of generators, how the risk profile can change. And this is an excellent tool in our hands to be able to predict the performance of a future electric power system, generating system. We are still on generation, remember. We have assumed the transmission and distribution to be fully reliable and capable of transporting the generated energy to the load points, to the consumers, correct? I also show you a very large system result, which of course you can only simulate using a computer. So this system has a capacity of 10,100 megawatt. What's the capacity of the system that we studied here? 100 megawatt, right? Or 200 megawatt, sorry, 200 megawatt. 10,100 megawatt, right? This is a large system, fairly large system, and it has some 300 and 500 megawatt units. So you see what we did? We changed the forced outage rate of these 300 and 500 megawatt units from 4% to 13%. And you can see the impact on the risk, yeah? And as you see, the profile is smooth. If you go back to this one, the profile is not smooth, yeah? So when you have a small system, the perturbations in the risk are significant. But you have a much larger system, the perturbations will usually be smoother. But you add a very large generator, if you add 1,000 megawatt generator, then this risk profile will not be so smooth. So all these factors need to be taken into account, but at least we have the tools, we have the resources to be able to come to a quantitative figure which we can use to justify any reinforcements. Okay. Now, scheduled maintenance, we haven't spoken about that. What happens now? We are using a COPT and we are saying this COPT is valid for the entire year or the entire month or the entire day. But what happens if one of the generators is on maintenance? Then either the load needs to be changed or the generating schedule needs to be changed, right? So maintenance can also be incorporated in our generating capacity reliability evaluation. It's not that straightforward, but it can be incorporated. So this is one way of finding the risk in the system by considering the maintenance schedules. So I'm going to show you this one first. So this is my load profile. This is the reserve in the system, and this is the total installed capacity. And let's say that these are the units on maintenance. Yeah. At different times, of course. You don't maintain so many generators at the same time. You can see that from this period to this period, these generators are on maintenance. Then this period, more are on maintenance. Why? Because this is a winter peaking system, isn't it? This is January, this is December. So where is the peak? The peak is in December and January, right? So it's a winter peaking system. That means you will tend to maintain the generators during the low load periods. And that's exactly what you're doing. Most of the maintenance is during the low load, not during the high load, right? That can be catastrophic. You wouldn't want to do that, okay? So when we consider all these maintenance schedules, then we can use this particular equation, the loss of load expectation, the risk, yeah, the risk LOLEA can be obtained by calculating the risk over these small little periods. So you'll have to do several calculations. One generator or two are maintained on are under maintenance. Then you use the COPT during that period, and then you convolve it with the load during that period. You will get one LOLE, right? So you'll get LOLE1. Then you do the same for another maintenance period and another maintenance period, and you sum them all up. You will get the overall risk in the system by considering maintenance schedule. So that's one way. The approximate way is this. Let's go here first. So approximate method of including maintenance is whenever some generator is on maintenance, I assume that the load profile is now going up by the capacity of the generator on maintenance. So for example, the generator on maintenance is 40 megawatt. The original load profile is the dotted line. Now I'm going to add 40 megawatts to the load profile, and I'm going to shift the load profile completely by 40 megawatt. Why? It is equivalent to the load going up by 40 megawatt, is it not? I have less 40 megawatt generation. Is it not equivalent to the load going up by 40 megawatt? I suppose it is. So that is one way of treating maintenance. You change the load profile, don't change the capacity outage probability table, and you get your risk index. That's one way. The other way is you have the installed capacity and then you know the capacity on maintenance, so you reduce your capacity, total installed capacity, to a new level. So your reserve in the system is much less now. So that's another way of treating this calculation using maintenance. So there's various methods available in the literature, and the treatment of maintenance is not easy in terms of hand calculations. That's why I have not provided an example here, just the conceptual way of how you will introduce maintenance, okay? Now, one more thing that we need to introduce is uncertainty in the load. We have so far been using, okay, 200 megawatt installed capacity, 160 megawatt peak load, right? But the peak load is not so certain. So how do you include the uncertainty in the load? We call it load forecast uncertainty, yeah? LFU, I'm going to use that acronym, load forecast uncertainty. So we know that some uncertainty exists in the load, which is described by a probability distribution, okay? Now research needs to be done. We need to know how the load is distributed in the future or in the past. So there is not too much data available, unfortunately, but the available data suggests that you can use Poisson distribution. I must have written somewhere, maybe on the next. Yeah, here. Published data has suggested that the uncertainty can be reasonably described by a Gaussian distribution. Of course, not everybody keeps data of the loads, and therefore uncertainties cannot be modeled very easily. So what we do now is we are going to compute the risk for each load represented by the class interval. So in other words, remember the normal distribution, there were plus 3 standard deviations, minus 3 standard deviations from the mean, right? So we are going to assume that the load that we are predicting is the mean, and then we are going to go minus 3 standard deviations, we are going to go plus 3 standard deviations. We are going to do the calculations 7 times. One at the mean, one at minus 1 SD, standard deviation, minus 2 SD, minus 3 SD, plus 1 SD, plus 2, plus 3. And if you recall the Gaussian curve that I showed you a couple days ago, we already know the area under those minus 1, minus 2, minus 3. Can you recall? And those areas actually represent the probabilities of the load being in that zone. So we already know that. Only thing we now need to know is what is the standard deviation. Again, we may or may not have the data, but the good thing is you can do some sensitivity study. You can assume standard deviation to be 1%, 2%, 3%, 4%, and see, you know, which appears to be more realistic to you. So that's what we are going to study now. So this is the table from the normal distribution. The mean value has the area of 0.382, plus minus 1 standard deviation. Each one has a probability of 0.242, plus minus 2 standard deviations, the probability is 0.061, and plus minus 3 standard deviations is 0.006. Let me show you this curve so that you can understand it better. So this is the Gaussian curve. If you are at the mean, this is the area under that, yeah, and the probability is 0.382. If you are at minus 1 standard deviation, 0.242, same as plus 1 standard deviation. So these are the probabilities, PIs, yeah. Now all we need to know is what is the time units that we need using that particular value. So using the mean, of course, we have already done the calculation, but we need to repeat the calculation 6 more times at minus 1, minus 2, minus 3, plus 1, plus 2, plus 3. So obviously this is more complex, it's more involved. So writing a small computer program will usually help. Yeah, and these days you have commercially available software for all of this. So I go back to an example to illustrate to you, which is always good for all of us to understand. Consider a generating system comprising of 12 5 megawatt 1% forced outage rate units. You notice that most of my examples I use identical units. Why? Because hand calculations are easier. you can use binomial. That's the reason. If I don't give you identical units, then you have to use the algorithm. Remember? Yeah? A times P prime X plus U times P prime X minus C. So it's a lot of steps, more work for you. Whereas this is binomial, so kind of easy. Yeah? The forecast peak load is 50. What's the installed capacity? 12 times 5, 60. The peak load is 50 with the load forecast uncertainty assumed to be normally distributed using a 7-step approximation. Actually, you will be surprised to know that researchers have used 49-step approximation of the Gaussian curve, and they found that the results from a 49-step approximation is not too different from that of the 7-step approximation. Reason is simple. We are capturing almost 99.2% of the information within the plus minus 3 standard deviations. So are you really bothered about the remaining 0.8%? Yeah, and doing it 49 times? It's really not worth it, but somebody has done it. So now we know that we don't need to do it, right? So let's look at the remaining data. The standard deviation is given as 2% of the forecast peak. So forecast peak is 50 megawatt, so 2% of that is 1 megawatt, okay? So standard deviation is 1. The load duration curve is represented by a straight line at a load factor of 70%. For those who are not familiar with the term load factor, it is 2 times the minimum load is 2 times the load factor minus 1, so it's 0.4. In other words, it's going from 50 megawatt to 40% of 50, so 50 to 20 megawatt, okay, in a straight line. The loss of load, the risk is what we are after. So if you do the calculations, you will find that at the mean value, what is the mean value of the load? The mean value of the load is 50 megawatt. At the mean value, which you can calculate, right? You have your capacity outage table using the binomial distribution, and if the peak load is 50, use the cumulative probability of 10 megawatt or more out of service, and you can get the loss of load expectation, right? So I haven't shown you that table, but you can determine that, and you will find that that is 0.0252396 hours per month, because the data is given for a month. Now, this is the COPT, and again, I'm not including any stages after this because it's already 10 to the power minus 8 or something like that, right? So, for the peak load to be 50 megawatt, these are the calculations. The risk is 0.025239. That's the risk. You can calculate using the cumulative probability table, okay? Now what I need to do is calculate the risk for 49 megawatt load, 48 megawatt, 47. Why? Because the standard deviation is 1 megawatt. So I'm going minus 3 standard deviations, I'm going plus 3 standard deviations. So I have to do the calculation 1, 2, 3, 4, 5, 6 more times. Until now I'm used to only one calculation, correct? Now I'm doing it 7 times total instead of 1 time. So you will find that the risk for each of these loads using the cumulative outage probability table, yeah, the COPT is 1 and only 1. That's not changing, fortunately. That's not changing, it's only the load that's changing. So you can get these numbers, and then if you weight the probability of each of these cases with the risk, then you will get the weighted value, yeah, expectation of an expectation, if you will. The risk itself is an expectation, right? So now I'm saying, oh, expected value multiplied by its probability of existence. So it's an expectation of an expectation, yeah? So the weighted value turns out to be 0.78. Do you remember the risk in the system when we did not consider any uncertainty in the load? The risk in the system was this, 0.025, correct? Now the risk in the system is 0.078, 3 times, more than 3 times. So load forecast uncertainty must be considered. Here the standard deviation is 2%, maybe it's higher, and therefore this risk will also be correspondingly higher, right? So we have the tools, we know how to calculate them, we know how to include them in our analysis, yeah? So that's the question you were asking me the other day about uncertainty. So this is one way of modeling the uncertainty. Okay. You want to take a break? Let me finish this 5 more minutes. Is okay? I want to finish this chapter. I think it's coming to an end, if I'm not wrong. Exercise for your doing pleasure. And now the load uncertainty is modeled like this. So you don't have to model it by a normal distribution all the time. It can be discrete. Yeah, depends on your data, right? Yeah, if your load uncertainty, you think that it varies like this, whereas the mean is existing for 75% of the time, but it deviates by minus 10 megawatt 15% of the time, and it deviates by plus 10 megawatt 10% of the time. The good thing about this distribution is you need to do the calculation only 3 times. For Gaussian 7 times. So I'm making your life easier through this exercise, okay? And I'm also giving you the answer. So, madam, I'm making the life quite easy, right? Well, one more question which is similar, yeah, very similar, but we are using a daily peak load curve, a straight line between the 100% and the 40% points. Again, the answer is given to you, so you can try that. Just summing it up now, the applications of generating capacity reliability evaluation. So we have seen how to calculate the reliability indices. We have the capacity model, we have the load model, we convolve the two, we get the risk model. We also know how to do sensitivity studies. We can change the peak load, we can change the unavailability of the generators, we can include uncertainty, we can include maintenance. In fact, we can add generators, we can remove generators. I did not show you the recursive algorithm for removing generators, but it is actually the same equation, except that you rearrange it for unit removal. Okay, so there's many things that one can do. In a more detailed course, we can actually look at all that. But I want to share with you on them by yourself relatively easily. At least that's what I hope. So the acceptable LOLE of 0.1 days per year has been used in many systems. If your calculated risk is worse than 0.1 days per year, it indicates the need to plan capacity additions. Or if you don't have the resources, you don't have the money to put more capacity additions, you might want to rely on purchases from neighboring systems. Maybe they're cheaper. That's why interconnected systems is so very important. We must rely on our neighbors and they on us so that we can share our capacity exchanges. And tomorrow, that will be the first topic tomorrow morning, interconnected power systems. Yeah, it's very interesting, very fascinating, obviously more complex as well, right? Or in the worst case, you still don't have neighbors that are willing to give you power, then what happens? Of course, the neighbors have the right? They can refuse. They want to feed their own first, not to feed their neighbors, right? So if that is the case, the worst case, you have to accept the temporary reduction in the risk. And you say, okay, at some time in the future, maybe I'm going to add capacity, but today I don't have the resources. So you just accept that reduced level of reliability. So we can choose appropriate reliability criterion, and if it is not a company, it's a pool of companies that they can also pool their resources. And the applications of quantitative reliability indices, there are many of them in generation capacity planning. And I've just listed a few here, which you can go through because you have the notes, especially to schedule unit maintenance. Because this is a very, very important field, asset management, as some of you have been saying. You want to maintain your assets, you must maintain them at appropriate times. When the system is experiencing the peak, you can't maintain, right? Even though your generators may be overloaded or maybe overheated or whatever, but you must try and get assistance and not maintain your generators, things like that. So it contributes to all kinds of things. You can calculate the reliability for a given expansion plan. You can decide what that expansion plan is, 5 megawatt hydro, 50 megawatt hydro, and things like that. And what is the reliability? You add generators, you know how to add generators, you know how to calculate the risk. Yeah, you can do it for 10 years, 15 years. So everything is at your disposal. We can calculate the system reliability level for acceptability before retiring any old generating units. There comes a stage when you have to retire some generators. I mean, we also retire, right? I'm closer to retirement than you are. Yeah, you are much younger. The word retirement doesn't mean anything to you. Yeah, but everything must retire. So when you are about to retire an old unit, hydro units probably lifespan 50, 60 years, same for nuclear units, yeah. When you are about to retire and the load is going up and up and up, and you have not installed enough generation in the past few years, then you can delay the retirement, right? As long as you have the tools to find out how degraded your reliability will be. And evaluate economic trade-offs. I mentioned yesterday about the cost-benefit analysis. So that's something that you must also do year by year, if not earlier. And you can evaluate the effect of reliability of new technologies. These days, we don't have just hydro, we don't have just fossil fuel, we have all kinds of renewables. So you must also consider those, the impacts of those new technologies, management of load, and improvement of the availability of generators through maintenance. So remember always that we have assumed, we have made a lot of assumptions and limitations, and some of which are due to modeling difficulties and others due to data limitations. Please always remember that. What I'm teaching you is not something that is exact science. Yeah, we must, as engineers, we always have to make approximations and assumptions. Okay, so a few more assumptions that we have probably gone through earlier, but just to complete the story, the generation reliability evaluation assumes internal transmission adequacy. I told you that when we deal with generation capacity reliability evaluation, we assume the transmission and distribution to be perfectly reliable. Now that may be a valid assumption when you are starting to plan your generation, but as the generation comes into operation, things change, and therefore you need to reevaluate your plans, right? So that's something that we must consider. Generating units are assumed to be running all the time unless they are on outage. May or may not be true. Yes, base load generators are almost always running, but not peak shaving units. Yeah. So therefore, we have to look at this in an operational manner also, which in this course we have not done. We have only looked at long-term planning, adequacy. That's why we call it adequacy. Finally, the loss of load condition defined in the planning studies may or may not result in actual load shedding. So we have been looking about capacity outage 0, 20, 40, 60, and we said, oh, loss of load, loss of load, loss. Maybe at that time there is no loss of load. Yeah. So there are so many uncertainties, and especially when we have the tools, we should be happy that we can model them at any point in time, right? And then the uncertainties in the estimates of the forced outage rates as well as the load demand would create an uncertainty in the calculated reliability indices. So please remember, the calculated reliability indices are long-term expected values. We don't even know their probability distribution. We just know the expectation, yeah, in the long term. So that's about it from me this morning, and then after the tea break, we have another chapter. Yeah. Thank you.